So in the last class, as I remember, we looked at hot working, cold working, right? And then this concept of strain hardening, right, which is very important when we are doing cold working. And then recovery, recrystallization, and grain growth. All these were looked at. Basically, these are part of the heat treatment process. We looked at a particular process called annealing, right? That's what we have looked at. So just wanted to have a video to give you an idea of what is hot working and how is it done, right? So we'll quickly go through what we had seen earlier in the last class, and then we'll look at the video so that we can summarize this topic and then move on to the next topics, which are basically sheet metal forming or stamping operations. Okay. So as you can see, hot working is when we are working with the metal or material at a temperature above the recrystallization temperature, right? So there's plastic deformation of that metallic material, right? In our case. So the highlight points of hot working are that there is no strain hardening, as I said, unlike cold working, because you are having a higher temperature, you're working at a higher temperature. Therefore, there will be no, not much dislocations. So there will be no strain hardening. That because of strain, you get hardening of the material or metal in our case. So strain hardening is not there, unlike cold working. Hot working does not have strain hardening, first point. Usually preferred at elevated temperature, as I said, because the metal softens, etc. Lead and tin are exceptions. They are having low melting point, so therefore they are generally not subjected to hot work. Lower limit of the hot working temperature is 60% of the melting temperature, right? That's the least temperature we can say, the lower limit of the temperature that we work. 60% of the melting temperature. So if the melting temperature is 100, then your hot working temperature would be 60, right? 60 degrees centigrade. So that's a comparison, right? Although the temperatures are quite high, right? 600, 700, and even 1000 plus for some metals. So that's hot working, right? That's what we have looked at. And then the different recrystallization temperatures for different metals, right? Tungsten being the highest because it is quite strong, of having much strength, and offers more resistance when subjected to loads, and it is quite dense. One reason could be seen as density. So as you can see, hot working, we looked at that there is no strengthening occurring during hot working because of higher temperature. Elimination of imperfections, gas pores can be closed. So if the temperature is quite high, then there is rearrangement of atoms. So gas pores can be closed, composition differences can be reduced, and even because of the mechanical loads, these gas pores can be closed, right? Because of application of external load. Anisotropic behavior is gained because if you are, for example, undergoing hot drawing, right? Depends. The different application areas, as we can see here, hot rolling, extrusion, and forging, hot drawing. So as for example, hot drawing or forging, the grain structure would be changed even for extrusion and hot rolling as well. So anisotropic in the sense you have elongated grains, the properties would be differing in different directions. That's what anisotropy is. The surface has a fine grain size and the center has a coarse grain size, right? So that's anisotropic behavior. The metal remains soft and ductile during the process. So now I want you to have a look at some video so that okay.
This is the process of hot working. There is a two kind of the working. One is the hot working and second is the cold working.
You see, they are being pressed, right, while being red hot, right? That's your recrystallization temperature being achieved. You separately increase the temperature of this material in a different furnace, etc., and then you bring it to the die. So these die also has to be resistant to what do you call? I mean, they should be able to bear the temperature that we are working in, and should be able to avoid wear and tear, right? There should be less wear and tear because they have to be used for long. So all those are kept in mind, keeping the temperature of this metallic material in mind. The dies would be designed, etc. So this is hot working, right? This is the state that we are working on with the material.
The process of the cold working, and in this video you are watching the process of
that's a crankshaft. If you have observed in automotives, right, either a two-wheeler or a four-wheeler, you would observe this crankshaft in the engine case, right? So that's done using this forging method.
The process of the camshaft making, and the process of the making a camshaft, and
this is connecting rod, making of a connecting rod
of the making a camshaft, and a CATIA and Roy and SolidWorks, so many kind of the software. Before the design of the camshaft, and then using so many kind of machines, hydraulic press machines, and now you can see this is the process in which they are pressing and cut out the required shape from different kind of the machines. And this is the hydraulic press roller.
That was rolling process. What you're seeing right now, it's called a rolling process.
Hydraulic press roller, and it's all work going step by step for a particular part of the camshaft from a particular process. And you can see this is the hydraulic press. Remove the unwanted material and give a proper shape. This one is also hydraulic press. There is a different type of hydraulic press according to the requirement of the work, and the whole process in which the metal is near 500 degrees centigrade or more than 500 degrees centigrade, but it below the melting point, so it's easy to convert the metal in any shape. So it's cold, hot working, and it's easy to convert a metal in a particular shape. So this whole process of making the camshaft of any four-wheeler engine, every part after the process of all kind of process from the different kind of presses, and after the hot working, then they go to the storage and finishing work. But just now you can see a small electric gears. These all are gears, and this is the particular software to use and making the design of required part of the engine. So in this video where you watching or see the metal in a red color, or it is a very hot, so this all we can call it hot working. This is hydraulic pressing the metal, the required force. This is amazing. Thank you.
Doubts? You see, all those what we have seen, either it be rolling or forging. I believe we have not seen what do you call extrusion here, but even that comes under hot working process, right? So no strain hardening, as we have discussed. There is no strain hardening, and even the temperature we have discussed, that the temperature is above the recirculation temperature, and about extrusion, let's see if we can because this is a separate topic in your 4th unit, but still because we are now looking at hot working process, will let us see if we can metal extrusion is what we want, but we can even look at plastic extrusion, no issue. Or let us have a look at the animation, because anyhow that will be inside closed eye. So I don't think we can find a real life extrusion process. Let's see if we can. Okay.
The primary type of hot extrusion is direct or forward extrusion. In direct extrusion, the hot billet is loaded into a thick wall container and forced through an extrusion die secured in a holder. The force for extruding is applied by a ram, along with an intermediate reusable dummy block. Metal flow from the die is in the same direction as the forward motion of the ram. Since the surface of the billet length slides along the wall of the container, extrusion force depends on the friction between the billet length and the container and the material. The friction portion of the force can be reduced by using lubrication. Force increases rapidly as the billet is upset to fill the...
Right, this is your billet, which is above the recirculation temperature, right? We are looking at this process in the context of hot work, right?
Container, then increases further as breakthrough force before extrusion.
So for this flow to happen, right, for this flow of metal to happen, you have to have the material at an elevated temperature so that you don't have much so that the material doesn't have much strength, right? That is able to flow as we want it to flow, right? So that's what that's where hot working helps us, right? So not just normal temperature, elevated temperatures we have to be working in, right?
Extrusion begins. Upon breakthrough, the force declines as billet length decreases until a minimum force is reached. As the billet thins, the force rapidly rises again to continue metal flow radially toward the die opening. Resistance to deformation or force requirements increase markedly as the thickness of the butt or unused billet portion decreases. Hot extrusion is most commonly performed on horizontal hydraulic presses. Hot extrusion presses are usually rated in force capacity, which translates to the amount of pressure applied to the billet. That pressure depends on billet material and temper, its cross-section and complexity, length and temperature, extrusion speed and reduction or extrusion ratio. The extrusion ratio equals the cross-sectional area of the container liner divided by the cross-sectional area of the die openings.
Nevertheless, we'll still have a look at the extrusion process when we are looking at fourth unit, right? But for now, I want you to understand what is hot working, right? And I believe that is now clear, right? As I said, all these processes, they involve hot work, right? Working at above the recrystallization temperature, basically. Hot rolling is not there in our syllabus, but still, this also is a major manufacturing process in the mechanical industry. You have the compression through the rollers, compression of this plate or pipe or whatever material that is, whatever geometry that is. You have the rolling, right? Compressive force being applied by the rollers onto the material. So this leads to a change of grain structure. This leads to a change of cross section. More importantly, that you have reduced cross section and you have increased density, as you can see here. So that's basically the gist of rolling, and that is used for producing sheets, as you know, metal sheets, sheet metals, right? So this is you can say sheet metal forming operations are preceded by hot rolling, because the sheets are produced majorly by rolling, especially hot rolling. So that's hot rolling. And then extrusion we have seen, right? That you force it through a die opening and the blank shape that takes the shape of the die, right? That's what we have seen. Forging also, in that hot working video we have seen that you apply compressive forces repeated, and they are basically impact forces. Generally, they are impact forces, especially in block forging. Press forging, you have more of a gradual load. Generally, rule forging also, if it is done. And hot drawing, right? This is also, I believe we have seen in the video, that you have you apply a tensile force to one end of the bar, so that the cross section of the bar will change because of the die opening, right? And you have different types: bar drawing, tube drawing, wire drawing. We'll see the different types in detail. But that's hot working. As for cold working, we are working at below recrystallization temperature, right? So there will be strain hardening. That's major characteristics. So I believe that is clear, right? Hot working and cold working. I could not show you some videos in the last class. Now we have seen them, so we can move on to the next topic. Now we'll look at sheet metal working, right? This will encompass all kinds of processes such as stamping, forming, right? Basically, it's a broad domain. Blanking, piercing, bending and forming, drawing, right? I believe drawing is there for even wires, etc. But there is cup drawing, right? Even those kinds, wire drawing, tube drawing, coining, hot and cold spinning. All these are processes that we'll look at in the third unit, right? So now let's look at what is sheet metal working. We'll see all of these. The cutting operations, the bending operations, all these are part of sheet metal work, right? Cutting of them, bending them, drawing, and some other miscellaneous sheet metal forming operations as well. Dies and presses for sheet metal processes, right? What are the different dies and presses? Sheet metal operations for not performed on presses. If you're not able to perform on stresses, or if you're not able to perform on stresses, presses, then there's other method to do. Bending of tube stock, right? All these things. Now, as for sheet metal working, right? Cutting and forming operations performed on relatively thin sheets of metal. As the name suggests, we have a sheet. Instead of calling a plate, we're calling it a sheet because the cross section is significantly less. The third dimension is significantly less than the other two dimensions, right? Cross section thickness is very less. So thickness usually varies from 0.4 mm to 6 mm. If you're looking at inches, 1/64 of an inch to 1/4 of an inch. So that's generally the working range of sheet metal processes, right? Thickness varies from so and so. Thickness of plate stock greater than 6 mm. Operations usually performed as cold work, right? Generally, these processes, what you're going to see, either be piercing, blanking, etc., they perform as cold work and not hot working. So you are working at lower temperatures, strain hardening, etc., would be present. You see, I intentionally kept this example here just so we can understand. This gives you an idea of what are the different sheet metal forming processes that are performed to fabricate or manufacture an aluminium beverage can, right? So the metal forming processes involved in manufacturing a two-piece aluminium beverage can be seen. So the first process being blanking, right? You have a big sheet and you want to have a certain portion of that sheet so that you can process it further. So that's what blanking is. You take out this, right, from a big sheet. You just take out a small portion of it. So this is, as you can see, the portion which we wanted, right, to cut, which is this. This is the blank, right? So we will have a distinction because there is blanking and piercing. The difference being what is your end product. If my end product is the one which the punch is removing, right? Basically this, which is our this circular what do you call sheet here. If this is my end result, then it's called blanking because we are getting a blank at the end. Blank is our desired result. Desired output. If the other part is your desired output and not this, then what you are doing is piercing. As for example, if I want to, let me draw here. This is my sheet. I want to remove certain portion. For example, maybe this portion and then this portion, etc. I wanted to remove. So first process, I remove this. In the first process, this is removed using a press. The shape has been cut out, right? And the second process, I remove the circular portion. Because my desired or end result or end product was this sheet, right? If this is my end result, the green sheet, then it's called piercing. P-I-E-R-C-I-N-G. The process is called piercing, right? But if the one which is being removed is my desired output, then it's called blanking, as you can see here, this process, because this is your end result, your product, desired output, right? So that becomes blank. Same process, same operation, but your desired output, if it changes, then your process name changes, blanking or piercing. I hope that is clear. No doubts, right? So you see, that's your first process. Okay, I'm giving you an overview of what we are going to look at in detail. But just so you can understand why is it important, why these processes are important, right? Important. So that's your first step, blanking. You've taken out a piece of metal from a big sheet. This is your end result, desired output after the first blanking step. Okay, cross section is this. If I cut it, right, I'll see this cross section, isn't it? As for deep drawing, as the name suggests, we're drawing it deeper, much deeper, right? Same sheet, it's being stretched to a certain limit. So you have to have a blank holder, right, which will hold this at the periphery, right? And a punch would come in and cause it to go down. So basically, that's your drawing it. Deep drawing, if your depth of drawing is more. So you can see here from this sheet, if I put a punch, right? If I place this in a die setup, hold it with a blank holder, and then apply force using a punch, then we can have this cross section, right? That basically you're trying to have a recess, right? So that's your cross section. This cross section gives us a better idea of what this product is. Although this is a 3D figure, it's quite not so easy to visualize. So the cross section will help us. Next, redrawing. So you are again, drawing it to much deeper level, right? Much deeper height. Then you have an increase in the depth, right? Increase in the depth basically. So this is your cross section after redrawing. Ironing, you're trying to have a constant cross section. That's what ironing does. It tries to even out the thickness, right? These walls, if they are not uniform, ironing process tries to make them uniform. As you can see here, much deeper drawing you can say, right? And you can observe that the base is still having a thicker cross section. I mean, the thickness is quite high for the base as compared to the sides, because we are doing ironing now. We've already done redrawing, and then ironing to level out the wall thickness. And then doming, basically trying to form that dome. If you have observed on the bottom, so that doming is done, right? This is a miscellaneous process. And then necking to form that neck. If you observe that carefully, on the top, right, is where you have the neck. Using spinning tools, because we even have those kind of processes such as hot and cold spinning, right? So using the same kind of tools, you would make this necking here, right? The neck of this beverage can. And then seaming, trying to have a combination, right, between different components here, right, different elements, right? So you have made that kind of can here, as you can see. So these are all sheet metal working processes, okay, in a nutshell. sheet and plate metal products. Where do we find them? Why is it important? Right? Sheet and plate metal parts for consumer and industrial products, right? Both for consumer appliances, you would use sheet metals, as you know. Not just appliances, even the regular, as we can see, utensils are also made of sheet metals, right? They are having a lesser thickness, right? So even that, and even your bakery trays, those are also made of sheet metals, right? So a variety of reasons, a variety of applications of sheet metals, both for consumer and industrial products as well. As for example, automobiles and trucks. In automobiles, you have the outer car body made of sheet metal, right? That's called BIW body in white, basically made up of sheet metal components, right? Trucks as well, you have a lot of sheet metal components, especially the outer body is made up of sheet metals, as I said. Airplanes, a very important application. The outer frame is made up of these kind of sheet metals, right? Railway cars and locomotives as well. The outer profile, the outer body of railways, farm and construction equipment. So there are a lot of applications, as we can see. Small and large appliances I was talking about, consumer appliances, office furniture as well, those trays, etc. I'm sorry that if you can observe that keyboard base, right? I mean the base where the keyboard is kept, the drawer, right? That is attached to the table using what? Sheet metal components, right? If you observe, there are pieces of metal and then there are rollers. So all those kind of applications, right? Computers and office equipment as well, as I talked about, different applications of sheet metal. So this is why we have to understand how they are formed, how should we form them, what are the different processes that can be performed to get a final product, right? There are many secondary processes, primary shape forming processes. Basically primary shape forming in the sense of rolling and etc. Right? And then the secondary would be to bend it, to either shear it, to have either some portion removed from it, like and piercing would come into picture. Then hot and cold spinning, basically trying to have a shape, right? I'm giving you a summarized version of those processes. But that's what is what we're doing with sheet metals, right? To create all of these, to create products for all of these applications.